Good morning, everyone. So today let's resume the second part of the lecture where we're going to talk about function calling. In the last class, we mainly focused on tools during the fine-tuning stage. So your whatever tools you want the LLM to be aware of, you'll have to create a lot of examples on how to use that tool. And once the LLM has enough examples for each tool, it will be able to pick up how to use that particular tool. Now, this is very limiting because, like as a developer or as a application developer, you might have like custom tools written in Python, or you might have a RESTful service that's running that serves a specific purpose. Now, creating examples for those and fine-tuning the model seems like a very tough thing to do, right? And it's not scalable as well. So that's where function calling comes into picture. Let's see how LLMs are taught how to adapt to functions and APIs very quickly. So before jumping into the details and defining what function calling is and how to build them, let's sort of take a step back and see how you would build a chatbot. Like you already have, let's say that you already have access to an awesome LLM like GPT-4, and you know how to use the GPT-4 through an API, and you are creating an application for, let's say, for application that students in IIT Delhi could use. And your goal is to develop a chatbot using LLMs and to have a conversational interface that supports, let's say, if you have any questions about the institute rules or policies, you should be able to answer. For the given semester, it should let you search or add and drop courses. And if you have any questions about like when these holidays are and whether a certain Saturday is a working day or not, you want it to answer. And similarly, let's say it even will let you know how much fees you'll have to pay for this semester, and an easy interface to make you pay the fees. Now, this is not a very unreasonable design for a chatbot, right? So you will have some information seeking tasks, and you will have some transactional tasks or even information seeking task that is not from a text but rather from a database that is exposed or a REST service that's being provided. Now, given that you know how GPT-4o works, like you give a conversation input and gives you an output, which part of these would be easy to create based on whatever you've been taught in this course so far? First and third. So why would first be easy? Perfect. So you have a document. If you index them, you could use RAG-like system to get it to work. And as long as you feed the retrieved document in the context in addition to your question, you should be able to answer it, right? So how is 3 easy to do? Does it look like it's going to be an easy job, or would it take like 10 minutes, or would it take like a day's worth of work to get it done? Because the first one seems like 10 minutes job, right? But the third one looks, maybe if there is some easy way to get it to work, it might make it easy for developers to do, right? So functionally, 2, 3, and 4 are not that different, right? Because if you have an API that lets you, or a SQL database where you actually store the courses that each student is eligible to credit and what they've registered for and not, then it would be easy to do too. Or if there is a REST service that lets you do that instead of a database, then like I mean like all 3 could either be a database or REST service, and 4 seems slightly more complicated because you'll have to authenticate, it has to be secure, and you'll have to trust it because it's not like it says one thing and does another thing, right? You don't want to like because the second one, even dropping a course or adding a course may also be slightly more tricky, right? But searching for a course and querying academic calendar, even if it makes a mistake, you can always like rephrase your query and somehow get it working. So let's see, and this is a very common scenario, right? Imagine if you want to create a conversational interface for a banking solution, or you want to create any task that you take, just pure information seeking based on document and simply conversing with an LLM is a very small subset of use cases that you could do, right? And if you look at it from an financial standpoint, right? Most of these information seeking queries these are not the heavy volumes in either a customer support or in any services that you would pay to get, right? Most of them are going to be transactional. Most of the information that will help you get money are all going to be stored in REST API, or backed by a REST API, or in a database and things like that. So if somebody wants to reduce the amount of, so what are the two ways in which you can save money? One is you build a chatbot so that there is no human intervention in between. It's available all the time. It saves cost. And if you have to do that, you have to support all these tasks, right? And second thing is, you don't want to, as a organization, you don't want to spend a lot of money in hiring somebody to maintain the system or even develop the system. If there is something that people can do quickly and they know that it's going to work, then people are going to use it a lot more, right? So for example, imagine in the old era before the web came into picture. Now advertising, like say your company, it's going to be a very tricky job, right? You need to figure out which board, which avenue you want to spend money on, what's going to give you better rate of like returns, like would it work, what is your demographic, you have to answer so many questions before you can advertise, right? But now it's so easy, right? You can have very specific targeted ads. You have Facebook, Instagram, you know exactly who these people are. If you know who your target clients are, it's so easy, right? So we want to get to that point for building chatbots as well. It has to be so easy that whatever you think of, you want to do it very quickly, right? So that's where the third one comes into picture. Like if you think like, oh, I don't know what all issues I would face, or how easy or difficult is it going to plug this in, then maybe that resistance will not let you create the chatbot, right? Because you don't know what you're getting into. And after you develop this, it doesn't work as expected, things are going to get more tricky, right? And you may even spend a lot more money in getting that working system. So the whole industry now has stopped worrying about natural language processing when it comes to LLM. Right? They're not worried about whether it understands your text or it responds back in a way that you want. They're more worried about how to make them do transactional tests, because any complex task you take has one element of transaction involved in it. Let's say even like most of you would probably use it to as a grammar correction tool while writing your paper or before sending an email or things like that, right? So imagine you can just type out, send an email. This looks good, send an email. Right? That might save you a lot more time, right? If it has access to your email, and just telling ChatGPT to send an email to your professor saves so much time, right? It might become more convenient to use. So if you have to get anything tangible, making it transactional is going to help you a lot, right? So let's see how LLMs are going to do that. So this is the sort of the whole architecture of how function calling would typically be used. A user comes, gives a query. Let's say in this particular scenario, you say, I want to drop 2 of my courses or things like that, right? So then your application will be the chat interface that you have, and it would be the server that's running your the application, and it would already have a list of functions that it can access, right? Like for example, it can have a API for calendar. It can have an API for adding, dropping, and searching courses. It can have a calendar for paying. It can have an API for paying fees. So it knows a bunch of functions that it's allowed to use. So all those will be defined within the application, and then it sends both the user query and the list of functions that it has to the LLM. Since now the LLM has the ability to use the functions whenever it's appropriate, it'll figure out which function to use for this query. It'll also figure out what are the parameters this function needs and what are the values that it should take, and then give it back to your application. Now, because LLM cannot execute the function, right? So the application, you might have a JavaScript code or a Python code or any interpreter, and then you would execute that API, get the results, give the results back to the LLM again, which would generate a response using the results and give it back to the user. So from a user standpoint, they don't know all these are happening. All they know is that they're just giving a prompt and they're getting a response back. So they don't care whether it's coming from an API, from a Python function, or everything is hard coded in the in your application layer, right? So now, why is this like so important, right? So let's say that you are Amazon Web Services or Azure Cloud or IBM Cloud, right? So your functions that you have is going to be deprecated at a such rapid pace. Every 6 months, you'll get a new functionality, new feature, and your functions will keep changing over time. And if you have to retrain your whole system every 6 months, it's going to be a nightmare, right? So So in this particular setup, as long as you just change the API specification, you should be good. Right? The model will adapt quickly. It's going to be so easy for it to, and it's going to be easy for developers also to maintain a system like this, right? Otherwise, it's going to be like so much expensive just to keep the system alive. You might probably spend more time in more money in creating the data rather than like saving cost by replacing a by replacing like existing services with a chatbot, right? So now let's see what happens. So like I mentioned, there are four important steps. In the first step, you need to define tools. So tools need not necessarily be like a REST API. It can also be a simple Python function like this, in which probably you access just a Excel file using pandas in the back, right? It can be as simple as that. And but irrespective of whether it is a Python code or a Java code or a JavaScript code or a REST API, you need to create a standard way of specifying what this particular function or API can do, right? So some simple things that you need to fill are just the name, a natural language description of what this function or API is capable of doing. Like this is the crucial part. If you don't give this, then the model will not be able to figure out when to pick a certain API or function. And in addition to that, you might have to give all the parameters that it would take and what are the required parameters, so that without that the model will not be able to execute that particular API or function. Now this is step one. You define the tools that are needed, and again, as an input you have to provide the user query as well. That's step one. And step two is that the LLM has to output something that clearly specifies what function to call and what are the arguments and what are the argument values that it could take. And this is done by parsing the user prompt, right? And so this is done by the LLM, and again, the application that you have, from an LLM standpoint, it doesn't matter whether the application executes it or the user executes it. So the LLM stops just by giving out the API call, and then let's say that your application executes it, it gets a status paid here, because the query there was what's the status of my payment, and they gave the transaction ID. The LLM gave you the right function name, the right arguments, and now you got a message back saying the status is paid. And finally, this particular input, this along with the query, when given to the LLM, it will be able to generate a natural language response back, right? It says that the status of your transaction with ID this is paid, and is there anything else I can assist you with, right? So these are the four steps. So now let's see how you would train such a system, right? So one particular task is like you give the conversation so far along with the current query and a set of tools that you have. Then your output has to be a certain way of figuring out what tool to call and what are the parameters and what are the values, right? So you have to create examples of this type for fine-tuning your model. Second thing is that you have the tool output and you have the conversation so far. You'll have to teach the model how to leverage, how to effectively use the tool output so that it can phrase natural language response. So this is the second task it has to know. And the third one is like, sometimes the user just says what has to be done and does not give you all the parameters, all the required parameters that are needed to call the model, right? So in that case, the model should be in a position to figure out which particular argument has not been provided yet by the user, and it should have the ability to pose it back to the user in a natural language form. Like here it says that, hi, I can help you with that. Can you please provide your transaction ID, right? So this is another thing, and of course there are a lot more other things as well. For example, if there are if you're a bookmyshow.com, you can say like, I'm bored, I want like get me a ticket, right? So now it doesn't know whether you want a movie ticket, it doesn't know whether you want an events ticket, you don't know, it doesn't know, like it cannot even narrow down to the right function call, right? Forget about arguments. So there'll be situations like that. So in that case, you should be able to help make the user understand that these are the different things you can book, and which one are you interested in booking. There may be cases like in booking.com, you can even say like, please order snacks along with that, right? Maybe it doesn't have an API to order snacks, so it has to handle a few more things as well, but these are the basic things that the model has to sort of be aware of. So now, so in order to create such a data set, so before going there, right? So whatever I talked about so far, GPT OpenAI models can already do these things because they have collected these data by themselves and already fine-tune GPT models to sort of do this, right? So now what the academic people and other companies which are more create open models and open data, they are trying to match what GPT-4 or ChatGPT can do already with function calling, right? So when I talk about these 4 different sort of works that created this data and fine-tuned the model, work has already been done for function calling, and OpenAI already has all these enabled. So if that's why if you see most of the baselines here would be GPT-4 or GPT-4 or ChatGPT, and what they're trying to do is to see if you are able to match up to that level of accuracy. So that's the goal here, right? So the first work that got really popular was called Gorilla, and what they did was they synthesized a data set named API bench, and the APIs or the functions that they used in the back are basically all the model cards in Hugging Face, Model Hub, Torch Hub, and Tensor Hub were sort of used. So each model would be used for a certain specific purpose. There are vision models, there are time series models, there are text-to-speech models, there are image generation models. So there are a lot of models. So each model has a use case, right? They can do certain set of things. So when a user comes and asks, I want to generate a cat image or something like that, then the goal here is for the LLM to figure out which model to call in which hub, and then give a small code that lets the user generate that, right? So that was the goal here, and they ended up fine-tuning Llama 2 7 billion model, and that model fine-tuned using the API bench data is referred to as the Gorilla model, right? So this is the overall picture of what they did. And one such example they synthesized looks like this. So our customer is a zoo, and we want to help them detect movement of different animals. Write a Python program in 1 or 2 lines to call API in TensorFlow Hub. So in addition to what they want, they've also given certain constraints, right? Which says that they just want it in TensorFlow Hub, and the gold API to call is this particular model, right? And since it's TensorFlow Hub, it has to be hub load along with other imports. And this is one of those models in TensorFlow Hub that will let you do object detection, right? And there are other parts to it which basically helps them generate better data. Now, so this is how the framework looks like. First, let's see the first part, which is how do they end up generating this particular data, right? So here, first, what they did was they sort of curated model cards that are specified in detail, and they match all the specifications which are not under specified, and they got around 1645 model cards from these 3 websites, and they converted them into a very common format, because each of the hubs would have different styles, fields, and things like that. And once they have that, they use so you guys might have already read about self-instruct, right? It might have been taught in the instruction fine-tuning classes. So they use self-instruct exactly that setup to generate, with in-context examples, generate more examples, right? And once they generated more examples, they fine-tuned the model, right? This is what the setup is. Now, so what they did was, when they created this data set, they also created a database which has all these JSON elements in them, right? Or basically they've written all these specifications here. So the reason why they have this is because because imagine you have 1645 API calls. You can't put all of them in the prompt, right? Because you have only a limited input space there, and most of these API definitions are pretty long. They describe a lot of things, they define all the parameters and things like that, so it may be really difficult to fit everything. So you need to first retrieve a very small subset of APIs that you feel are relevant for this task, and then let the model decide how to use them, right? So here the user says, I want to see some cats dancing in celebration. So then the retriever would sort of get some relevant APIs from the database, and then give that API specification to the LLM, and the LLM along with the input question would be able to generate the API, which when executed gets you the result that you want, right? So the good part about this paper was that they said that it's good not to let the model memorize all the APIs that you have, but rather provide them during runtime so that they don't overfit on that particular specifications, right? So when you adapt your API or when you change your API, let's say you, like everybody releases new version of the model all the time, right? So now when new version comes, you should not be stuck with the old version, right? So that's why they say that in here they do some experiments to show even if they change their model name, the performance doesn't drop, right? So that was one, and that is achieved by using the retrieval augmented training, right? So this was one of the main contributions, and the other contribution that they made was that they came up with how to evaluate these models that can do function calling, right? So the output of most of these models are programs or like the APIs that they are supposed to call along with parameters. So what they mentioned was that there are certain cases, like for example in Python, you might have default parameters, and you can change the, if you provide a variable name, you can change the order of the variable names. So strict string match is not probably the right thing to do because you will miss out a lot of right things. And so what they said was they borrowed from the programming language literature, where if you want to compare two programs, rather than comparing their surface forms, you create a syntax tree and then you compare that, like abstract syntax tree, and compare that. So that's what they introduced here. And then they also came up with this way of figuring out where the model fails, right? Rather than just saying we only have an AST match accuracy of 60%, they also said that where exactly are we failing. So they divided the failure cases into two parts. One is that you are hallucinating, in the sense that you are giving out API names that don't even exist, right? They are not in the retrieved list, they are not provided as a part of the context, or you are cooking up arguments that are not a part of the function specifications, right? So for example, in this particular example, there is no possible value for the second parameter that can take ASR, because it's an enum type. There are only certain specific values it can take, and ASR is not one of those values. And secondly, there is no optional parameter called source, right? So this is clearly hallucination. So what they say is like, if the model outputs an acceptable function that is given as a part of the input, then it's a wrong library. So the failure is because its understanding was incorrect. Maybe the description was not right, it was confusing, maybe the user utterance was confusing, there are other reasons for it. But if the model hallucinates, then we know for sure it's a model problem. Like, it's not any other problem, because there is, under no circumstances you're supposed to hallucinate, right? You can't cook up function parameters and function names, right? So this helped them to sort of narrow down where they should focus on in the consecutive iterations of their model training. So if you see here, so they have two different experimental setup. One setup is that where you provide retrieval results based on a real retriever system, right? Where it may so happen that sometimes the right API that you need may not be there, and sometimes it may be there, right? It's most likely that it's going to be there, but it will also mimic failure cases. But and this one is the Oracle scenario, where the right API or the function is always present in the input at any point in time, right? So here, if you see that at that point in time, Llama did not support function calling, and so its output was like the overall percentage of cases where it helps is less than 15%, and most of the time it hallucinated, right? So biggest issue was hallucination. It was not even like incorrect incorrect detection. And then if you see models that have been trained for function calling, their hallucination is very low, right? But they have errors, they're making semantic errors, they're picking the incorrect APIs and things like that. And what they show is that Gorilla doesn't hallucinate as much in this particular setup, and most of its errors are coming from like just picking the wrong APIs or wrong APIs most of the time. So similar analysis were done for other data sets as well, and the summary is that in most of the times the hallucination rate of gorilla is much lower than other models on an average, right? And the other important point to see here is that this helped them figure out that GPT-4 in many cases hallucinated more than GPT 3.5, right? So this also pointed out some of the issues in models regressing in certain cases. I think now after the first version of the paper got released, then GPT-4 actually corrected itself, and now their hallucination rate also has gone down significantly. So in addition to releasing the Gorilla, the data set and the function calling model, they also created a leaderboard, because they soon realized like it's hard to figure out which models are doing good, which models are not doing good, and the sort of data that they had was very limiting. So at that point in time, they released a new data set called Berkeley function calling version 0 of the data, and they had few tasks. But then as and when the field progressed, they released this first version, second version, and now they have the third version as well. This has become sort of the standard place to track how GPT is performing, how latest version of OpenAI models are performing, Google's Claude are performing, and also how good are these new open source models that are performing. And so this has become sort of the benchmark to figure out which models are doing good function calling and which are not, right? Now, so the summary of API Bench is that the diversity of APIs are very low, even though they say that if you change the names of the parameters and names of the functions, it still works, but still it works within the domain, right? It's low diversity, and it's not very complex. Like it could not do what we initially discussed in the motivation. It can't do a full-fledged conversation. You just give the input utterance, it can give you what API or tool to call. That's about it, right? So it can't converse with you. There were a lot of limitations for this. And so then came the tool alpaca data set. So again, if you see, all these papers were published around mid 2023. All of them sort of came in parallel, right? So here, rather than using a very small number of APIs, they got a lot more real world inspired. The inspired is very important here. Inspired tools that spans a lot of categories. And again, once they had the data, they fine-tuned a Vicuna model here rather than a Llama model, and they created their own version of function calling models. So when I mean real world inspired, what I mean is that they only got the tool name and the tool introduction or a small description about the tool by scraping the web, but then they sort of synthesized everything else. So given the tool name and the short description, they ended up creating a little larger description of what this tool would be capable of, and post that they came up with names of function or APIs that you could have within that tool, and then they also came up with detailed specifications of how to call the tool and what all parameters it needs and things like that. So this is inspired because all these are not picked from a real specification. All of them are picked up, right? So, but the good thing about this is that they created a really nice conversation which could get you an end-to-end function calling model ready, right? So it's able to figure out that there are certain places where you have to chat with the user, and the reason why you need to chat is that you need the user to provide with a year for this particular setup, because the user wants to know the holidays of Japan next year, but the model is unable to figure out what next year here means. So it's explicitly asking for the year at this point in time, right? And when the user says 2024, it's able to figure out that now it has enough information to call get holidays, and here are the parameters and the values, and then it executes it, and then it's able to generate the right response back to the user, right? So this is slightly better than what API Bench had. It's a little more diverse, and it simulates the whole thing. So then these guys did an evaluation of tools that they did not see during train, right? Because the previous Gorilla approach, all they did was they changed the arguments and measured, but here they're changing the tools, and they also picked a very small subset, I think 10 or 12 real world APIs, and generated conversations with them, and then checked how these models perform. Again, as expected, GPT 3.5 was sorry, GPT 3.5 was much better, and at least tool alpaca 7 billion and 13 billion models were trying to bridge the gap compared to the non-function calling version of the model, right? So they are moving in the right direction. They are pretty close, but still there is a long way to go. There's at least 10 points difference here, 5 points difference here in the overall setup. Now, yeah, so like I said, the tool alpaca dataset had higher diversity. It had 400 real-world inspired APIs, and it now has multi-turn dialogues which could support question generation and response generation as well, in addition to just figuring out what API to use and what parameters that you should provide. So then came tool LLM, where in addition to we saw API bench, tool alpaca, now you have tool bench. So here these guys scraped real world REST APIs from a website called Rapid API Hub, and they scraped about 16,000 real world APIs and generated data based on that, right? So this moved a little closer towards a more real life scenario, but still they ended up synthesizing the conversations, right? Again, they created using their data set, they again fine-tuned Llama 7 billion and called it Tool Llama. So the good part here is this particular setup, that they actually got real world APIs and developed conversations on top of that. So this will, so because you had a certain assumptions about how APIs would look like, and you had a very specific way of generating API descriptions and API specifications, you might not have hit a lot bottlenecks when you generated the dialogue. Because you would have been, because if everything is of a same format and there are no and everything is like very clearly defined and it all follows the rules, then you would not face obstacle in this stage where you actually end up creating the dialogues. But now, since you are scraping real world things, they soon figured out that it's not generating as good dialogue as the previous approaches did, right? And so what they did was that they generated dialogues in multiple phases. First, they generated only the first instruction, what the user might start the conversation with, by taking a small subset of APIs, figuring out if you are given these APIs, what sort of queries would you be able to answer. They prompted this to an LLM, and specifically ChatGPT, and then they got some instructions, and they also figured out what subset of these APIs would be used for the conversation. And what they soon realized is that once they create one or two utterances, some of these APIs were not linked right, or they don't have enough description. For example, the description about the tool would be empty. The arguments would just say the name, like variable 1, variable 2, rather than actually defining the variable names, and there would be no description field. So like the model was not able to make sense and then use information from that API description to actually generate something that's meaningful, right? And so they came up with an approach in which they can sort of make it better, right? And that's where this new technique of generating data came in. And once they used that, they ended up creating the entire data set, which when fine-tuning on Llama gives you Tool Llama. And the good part here is that as a byproduct, they were able to train a really good API retriever. So before that, people used retriever systems built for certain other applications in mind. Like for example, they used BERT, even though BERT was not specifically designed for retrieving, or most of the extensions of BERT, right? Where they were not specifically done for retrieving APIs, but rather for documents and similar documents, or query and documents and things like that. So they were able to generate a really good data for training a retriever, and they were able to train a retriever as a byproduct of this, which became a very useful tool later on. So this is how they generated the data set. And during inference, it's very clear, right? Like once you get the first user query or the conversation, you query use the API retriever to get a list of relevant APIs, and then you figure out what APIs to use, and then provide the final answer back to the user. So coming back to synthetic data generation, before this simple, I'll start with the first utterance. I'll generate the agent response, and then I'll again do what tools I should call, and then I'll come and then I'll finish the dialogue. That was what, like a single path, if you take, you would end up getting a good dialogue, right? But that was not working anymore because the APIs were not right. Maybe they were not giving out meaningful responses back because the response doesn't make sense. The input also is so screwed up. So you end up getting some garbage, and that sort of screwed up the conversation following that, right? So they had to figure out some sort of a depth first tree search where they got some rules about what is a normal execution. They figured out like, okay, it executed well, it did not execute well, it's giving out meaningful trajectory, it is not giving meaningful trajectory, and they had a really detailed flowchart about how they would figure out something is normal or failed. And once they hit a failure or an error, they would backtrack to the point where then they did go sample something again and then explore a different path and things like that. So they said by doing that, they were able to save time and also get at least one successful path at some point in time, rather than a lot more failures, right? And this way, they were, and at every stage, they were actually leveraging Chat GPT to make a final call about whether they should stop, go back, or what they should produce. So for almost all generation purposes and decision making purposes, they used LLMs. All they are saying is that, like if some tool fails, now look for a different tool, right? If this particular generation did not give you the right sample, maybe the argument was wrong. Maybe you had to give a value from a certain enum that was not specified in the API specification to begin with, right? So maybe you generated something you didn't accept because the argument type was not right. So try generating 2-3 samples again. Maybe one of the arguments would match what the API would actually agree, right? Accept. So these were the things that they tried. It's just a pictorial representation of like going back to the point wherein you failed and trying it again, right? But in the usual case, you never assume, you never had to encounter a failure because everything went smooth as expected because everything was fabricated or synthesized, right? So now, even though the data set they created is called tool bench using the rapid APIs, but these guys wanted to see if I use API bench, which is the Hugging Face model hub, TensorFlow model hub, and Torch hub. If I run it on that data set in which this model was never trained on, then how good or bad does this model perform? And what they figured out is that if they use their version of the retriever along with their model, it was doing good job on 2 of the subsets of the data, and on 1 it was doing almost equal to what Gorilla, which was fine-tuned for that particular data, was doing, right? So it showcases how general purpose the model has become now compared to what Gorilla was trying to do. But again, there is a small nuance here, which is they have conveniently changed the retriever. This retriever is a lot better, right? And this retriever is one of the basic retrievers that you could have, and it has a lot more failures than their retriever. So by face value, we can't take that Tool Llama is better. It just says that the combination of Tool Llama and their retriever is better than a very basic retriever and Gorilla, right? And so to study that better, they used Oracle retriever. So the APIs that are needed are always there in the context, right? In that case, you can see that the model that is overfit for that use case is slightly better. But the good part was like, this is not that far away, right? So this proved that we are going in the right direction. The models that the data sets that are now being generated and the models that are now being trained with these data sets are able to generalize to out of domain APIs. So this sort of gives us the right model where if you have to create your chat application and you want to introduce your own API, then you can use Tool Llama along with their retriever. This will probably give you a better starting point than anything else. So now, like we mentioned, now their diversity has increased a lot. Initially, the previous dataset only 400 real-world inspired APIs, but now we have 16,000 good APIs, and dialogues are also multi-turn. But the reason why I have not clearly put with question generation and response generation is because it is sort of restricted in a way Chat GPT can interact, right? Here they were able to generate really nice questions because they had very specific prompts for generating each of these particular type of agent utterances, right? They had coordinated it very well. But Tool Bench did not do a really good job when it comes to dialogue generation, like mainly because they were overwhelmed with the unexpected quality of the real world APIs that they crawled, right? And so if you actually look at the data that they've generated, it doesn't look as clean as what you want the model to learn, right? And but on the other hand, they had stepped up in one direction where rather than using a single tool, they also explored the possibility of using multiple tools within a conversation, right? because it sort of looked in many cases that a single tool is not something that would always be needed. There may be cases where you have to chain 2 or 3 different tools or call multiple tools side by side and then figure out to get to your response. So now the three work that I explained so far were all done in mid 2023, right? Right when OpenAI came up with this function calling. But then in 2024, mid 2024, people sort of had done like enough good work where they were able to generate much better data. There were a lot of good open source function calling models that were performing almost as good as GPT-4 and Claude on Gorilla leaderboard. So this paper is one of the recent papers, and the reason why I picked this paper is because they open sourced all the data with licensing that lets you to use it in commercial purposes or any purposes, right? Because most of the models or the data creation pipeline that I proposed earlier were all using ChatGPT or GPT-4 synthesized data, right? So that's a problem because you can only use it for academic purposes. You can't use it for any real world purposes, right? So it was always limited by that. And so very recently they released this data, and now anybody can train their own function calling model. And they also trained they trained 4 function calling models. There were X large action model, which was 1 billion. They also trained a 7 billion model based on DeepSeek coder models, and they also train Mixtral based models for these action for function calling. Now let's see what they did good, right? So of course, after looking at the previous data set that was developed using Rapid API, everybody clearly figured out that the multi-turn data that they created is sort of not that usable. So you can't really deploy it in real world application. It's going to give you junk most of the time, even though on metrics it looked good, right? But the conversations are so bad, right? So that's not something that's usable. So they figured out that you'll have to create clean conversations for this thing to work, right? And the way to create clean conversation is like, while they filtered just based on API execution, these guys started to filter like even at the dialogue level to see whether you're generating meaningful dialogues or not. Does it look natural and things like that, right? And so one of the contributions is that they sort of have a very detailed verification phase, right? So here what they say is that first they used the same API library that tool bench had, which is the 16,000 Rapid API specifications. But one of the main reasons why that failed was because most of the APIs were not right. So first thing they did was reduce 16K to 3K. They used a lot of rules and figured out like there's no description here, this doesn't execute, this is deprecated. So they removed all of those things and made this clean. And once they had it clean, they had some seed QA which would serve as few short examples, and they generated a lot more data points. And once they generated question answers, they had a very clean verification stage that gets you clean data, right? Let's see what these verification stages do. The first thing they did was just like how the first Gorilla approach did, that they created a very clean format that sort of is uniform for all the tools. They also created a similar uniform format for all the APIs and functions they had, right? And this is an example of how an API should look like. This is an example of how a function should look like. And what they did was they generated output from the LLM also for a JSON format, because at that point in time, most of the LLMs were really giving out nice structured outputs. If you ask them to generate something in JSON format with a certain schema, they did that, right? Before that, they were not. Most of the open source models were not doing that good a job, except for OpenAI models. But since now LLMs have seen a lot of code and they've been fine-tuned for these generating outputs not just as text but as JSON with a certain schema, they were able to do a good job. And because of that, generated output became a lot more structured. Now, once you have structure in your input and output, you can write a lot of rules to clean things up, right? So for example, if you had hallucinated some parts, you can actually figure out that you have hallucinated. Because you have structure and input, structure and output, you can see that if there's an enum in some parameter value and that enum is not followed, then we can reject that sample, right? So there are a lot of very simple formatting based checks that they were able to do with a new version of LLMs. And so they were able to leverage that and remove a lot of data that were not following the certain format. Now the second thing is, while the previous approach, while synthesizing the data, figured out that executions were failing, they also did the same thing, like execute that Python function or call the REST API service. If it gives you a good output, then don't filter it, but if they don't, then remove them off, right? So that was easy. And finally, they also had a semantic checker, which is, this was something that previous approaches were not doing, which is you assume that whatever API has specified in the description is right. Sometimes it may not be right? And secondly, it might so happen that the model gave back some junk, but you interpreted that JSON in some way and you generated some results. It just is not making sense. And because you're trained to assume that it gives you the right JSON back, which has the right information necessary to solve this task, you would use that information in one way or the other and then phrase your answer, right? But that may not always be the case. So they sort of used an LLM as a judge to just see the question, that the last response is generated, and then say, does it look like a cohesive conversation, right? So this sort of helped them figure out what all dialogues were not looking like natural, and they removed all those things, right? And if you see here, this was a really good analysis table that they released, which is, these are the different models that they used for synthesizing data, right? And they said that they generated 40K examples from each of these models. And what you see here is that DeepSeek version 2 chat was able to give them a lot more good data than any other model, right? And they show you exactly where they fail. Like formatting was a big problem with the 33 billion model, and Mixtel 7B also had a lot of formatting issues. They were not able to generate output in the right format, whereas the bigger models were able to do a good job. And execution failure, semantic failure. So this is a good part, right? So the actual dialogues generated by DeepSeek V2 chat was so good that they didn't have to remove the dialogues that were generated. They were all looking cohesive and natural, right? So this was so then they were able to figure out what models to use for generating your data rather than blindly using all the data generated by the model, right? So please note that this still doesn't mean the 33K is perfect. It just means that it has crossed these filters and reached this point, but still there may be issues there as well. But at least it's not as bad as what it could be. Now the good part about all these have permissible license, so you don't have to worry about using them in your projects, whether it's for monetary or research purposes. So now the model that was fine-tuned using this API Gen library quickly reached one of the top positions in the leaderboard, right? And if you see here, this is a 8 cross 22 billion model. It's not as big as what GPT-4 or GPT-4o is, right? And I technically GPT-4o might be slightly smaller model as well. It might be distilled, but it was able to achieve that. And they also have a XLAM 7 billion version, and an XLAM 1 billion version, and they're also like way ahead of many big models, right? So the summary here is that now XLAM function calling dataset, which was generated using the API Gen framework, has now really diverse, clean data, API data, right? Initially you had 16K not so clean data, but it looked like it was a good direction to go. But then these guys figured out that it's good to have high quality data rather than having a lot of bad quality ones, right? And that was the thing that helped it boost to higher up in the leaderboard. So this sort of follows the principle of Lima, where they say that small number of good quality examples are always better than a lot of moderate quality examples, right? And their high quality is reflected not just in the APIs that they use, but also in the dialogues that they use to fine tune the model. And in addition to whatever these guys expanded, and the type of dialogues, these guys expanded it a little more based on what real life situations needed. Like for example, sometimes you call single tool, sometimes you call many tools in your conversation. And they also figured out that, let's say if you want to book flights, it's not necessary that there exists only one API that lets you book flights, right? There will be like thousands of APIs that can let you book flight. But then if you are confused at that level, now the nuances are so small that you have to pay a lot more attention to what specific things the user wants, right? So they created examples of those type, and they made the model do finer grain retrieval and using them. So these are the most common popular open source ones. And now I'll also talk about, in the same time when API Gen came, we at IBM were also working on open sourcing our models, and the same issue that people had faced earlier was one of the reasons why we also started working on it. We wanted also to create open source data so that the models that you develop can have Apache license and anybody can use it without having to get permission or without having to worry about using OpenAI's generated data, right? So we were and at that point in time, most of the open models did not have right licensing, right? For example, Gorilla or Tool Alpaca, all were based on Llama, which cannot be again used for commercial purposes without proper licensing. And also the data sets were all created using ChatGPT or GPT-4. Again, you cannot use it for any commercial purposes, right? And the second thing is, like, even though these guys did out of domain tests, they were not exhaustive, right? They did it on, like, say, one of the tests was that they did it on the tool hub, the hub, all the model based data set, but they did not do on a held out large scale data set, right? So one of the papers that we wrote showcased that even though they claim good out of domain generalization, but if you take a slightly larger set and then evaluate, none of these models generalize well, right? And the third issue that we were dealing with at that point in time was that most of these function calling models assumed that you would end up building a solution with LLMs, right? But typically people don't do that. What they do is they already have existing chatbots that they have designed using statistical plus rule based approaches, which are very interpretable and predictable, right? So they don't want LLMs to make decision all by itself. Like, I want to call this API and this is the only option I give you with all these parameters fixed. Now, if I cannot call this API, I'll just give you the natural language version of what you should ask to get more information. So this does not give enough control for somebody to design a chatbot, right? So people wanted access to, application developers wanted access to specific parts of function calling. They just wanted it to say, no, give me what is the most likely tool that you would use, right? Or I know what tool you have to use, like, and you just give me the parameters. So when you started using LLMs to do only specific part of the function calling tasks, then these models were not doing a good job. And we had empirical evidence to show why they were so bad. Like, even though the AST accuracies would be in 90s, the single task accuracies will be in 30s or 40s, which doesn't seem to make it usable. So in parallel to API Gen, we were working on synthesizing our own version of the data using open models again. We were using Mixtral and some Flan XXL, and for simple tasks we used simpler models. For more complicated tasks we used slightly bigger models. And again, we also repurposed. So everybody was synthesizing data, but there were a lot of task-oriented dialogue data set that have been made available and collected by humans for a really long time, like from early 2000s. But nobody were using function, like those are actually calling functions, task-oriented dialogue data sets, and they were designed by humans. They were inspired by real-world applications, and we repurposed most of those data sets for function calling purposes, right? And then we also synthesized data with the more open version of the model, and we created tasks that support granular tasks as well. And with that, we were able to get out a 20 billion function calling model, which was again open sourced, along with the data set that was used for training the model. The good part about this data set is that it is more friendly for application developers, like, because it supports all these granular tasks, which if you want for your application, you can always call. You don't have to necessarily do the whole function calling thing, where in case you just want to generate a response with a certain JSON that you obtain through some other means, you can still get it done. If you just want the top K list of intents or the APIs that you are likely to call, you can do that. The other reason why this was helpful is because sometimes an enterprise will have 20-30 different chatbots designed by 20 different applications, right? So these are not functions, but still you want that small functionality which lets you decide which API to call, right? Which will give you, in this case, it will be which tool or which chatbot to call, right? So we sort of decoupled all those things so that it's now a lot more easier to develop more flexible chatbots by leveraging large language models' ability to understand language and process language, and at the same time also use your traditional systems to sort of patch everything together to make a single composable system. So currently we're also working on, during the time API Gen was released, the Granite model was the top open source model on the leaderboard. But now again, API Gen is a lot better than what we're doing. Okay, so this is a summary. We've covered 4 different ways of generating synthetic data for function calling, and at this point in time, it looks like API Gen is leading the road. And we also talked about some other work that we are doing in our team. Okay, thank you.